I'm going to do another demo today. The last demo, I showed you how to do a very basic optimization. Tried not to get too complicated here. So we're going to go add a little complexity, build on what we'd learned last time. In particular, I'm going to look at these four things. Um, one, and some of these you've been running into with your homework and some questions have come up. So one, for example, what if I have a function that has additional parameters, not just design variables? How do I handle that? Or often will be the case that the objective and constraints are contained in one function, but fmincon wants them separate. So how do I deal with that? Post-processing, how do I look at my outputs? How do I maybe plot things like convergence histories? And then finally, we'll look at a few more options. We just looked at one last time, but we'll look at a few more options. Okay, so the problem we're going to solve is actually the exact same one as last time. That was a simple two-dimensional problem with two constraints. Although here what I've done is I've written it as if it was some engineering code. And so I'm calling this function structure. It's going to take in some design variables and some additional parameters. And it's going to return a mass and some stresses. And these are obviously not really masses and stresses. It's the exact same problem as last time, but I've just written it as if it was that way. So this is something, you'd have some analysis code, and in general, it's going to return maybe many things, and it's going to take in potentially many inputs. Okay, so yeah, so and for our purposes, we don't have to really worry about what's happening in this black box. We just want to be able to optimize this. Okay, so I've got this function structure. I'm going to want to call fmincon as always. And fmincon is going to need a function. So it's going to want an objective function, starting point. These are almost always going to be blank for us. We won't have many linear constraints, although if you do, it's nice to take advantage of them. Lower bounds, upper bounds, nonlinear constraints, and then options. Okay, so that's just our regular function signature. Let's just get started with the normal stuff that we're used to, a starting point. Let's just say we're going to start at 3, 3. We don't actually have any bounds, although it's good practice to just put them in. In this case, we don't have any, but if you did, they'd be the same kind of format. We'd have 2 lower bounds for the 2 variables, 2 upper bounds, and we could put them in. Maybe let's just put them in this case. Let's say this is a real structure. We don't want it to go below 0 and maybe not above 10. Okay, great. So I've taken care of the easy things. Now I need to define an objective and a constraint function. Although my challenge here is that this structure, this is the function that I want to call, it just paste it here. It is returning mass and stress, and whereas the objective function, it only wants to have an objective. Okay, so it can't have other things. I can't just pass structure into here. That's not going to work. So I need to create a function and call it objective. It needs to do something like this, right? And the return is just going to be the objective function. So what I could do is not actually what we're going to want to do, but I could do this. I could call the structure, and let's ignore the parameters for now. And then I just set f equal to mass. It's no problem. I just ignore the stress part. I could even put in a tilde if we wanted, right? That's the Matlab thing to say ignore that output, but it's not going to matter. And then, oops, I'm just going to copy and paste that. For my constraint function, it wants the constraints and the equality constraints. And I could do something like my constraint is going to be stress minus stress max, because I'm doing the less than or equal to convention. That's what Matlab wants. And then I don't have any equality constraints. Okay, so I could do something like this. This would work, setting aside the detail that I'll get to later that I haven't defined parameters or maximum stress, but that's not yet important for what we're trying to figure out. Okay, so if you notice though, there's one big downside to this. The downside is that often, though not always, I'm going to call my objective and constraint one right after the other. So I'm going to give in some design variables, The optimizer is going to choose some design variables called the objective, and then it's also going to want to evaluate the constraint at the same x. But you notice that I'm then calling this function then twice. So this is going to roughly double the cost of my optimization because I'm calling stress here, but I don't need it here. I'm just throwing it away. And here I'm calling mass again, but I don't need it. I'm just throwing it away. So we want to be a little more clever about it. There's actually a web page. So if we just did a quick search for, say, Matlab, objective and constraint, same function or whatever, just do a web search. There we go, this first one. Here's some detail about how you could do this. And I'm going to do basically this exact same method here, but you can just Google this and refer to this so that you can maybe copy and paste some things, but I'm just going to walk through it blank here. So let's do that. What I'm going to do is I want a function. What I would really like is I wish there was a function. Let's call it objcon, okay, objective and constraints, that handled both of these at once. Okay, if I had such a function, if Matlab took such a function, then I could have just called structure. And then I could have parsed out the different pieces. Let's just copy and paste these. Okay, just like that. All right, so then I took care of everything in one shot. I don't have to call my analysis code twice. But that function doesn't exist, so I'm going to create one and rewrite these objective and constraint functions so that they use this in a smart way so that they don't repeat effort. Okay, so here's what I'm going to do. I am going to keep track of the last x function, x value that was called. And if that x value is the same one that I just used, the last one that I used to call my structure function, if it's the same one, then I am not going to call my analysis again. I'm just going to use a value that I saved. So in other words, I'm going to save my outputs, mass and stress, or my objective and constraints rather. I'm going to save these. And if x is the same, I'm just going to give it to it. And if it's changed, then I will call my analysis. So I only will call analysis when x changes. So the way I need to do that is I need to store these variables. And probably the best way to do this is I need to define some functions in the outer scope. So I'm going to keep track of my last x value. And I'm going to keep track of my last function value. I'm going to keep track of my last constraint value and the last equality constraint value. I'm just going to save these. Okay. For this to work, I need to have a nested function because I want, Matlab is complaining because of the order it wants functions to be, but I want to be able to access these variables inside of this function. I don't want to make them global because I don't want to access them anywhere, just within this function. So I'm going to call this whole thing, I'm going to create a function around this whole thing so I can use a nested function. We call this a closure. It's a little cumbersome in Matlab, but it's the same. This will work in any programming languages with different syntax. Okay, actually I don't need an argument here. So now that I've nested these functions, I can refer to things that are inside here. And notice they turn blue. That's just letting me know that, for example, these are, let me just write it out. Okay, so here's what I'm going to do. If my x value is not equal to the last x value, then I'm going to call my function again. So there's a function called is equal. I'm going to compare x and x last. So if this is not equal, and you don't have to necessarily memorize this, you can go look on that web page I showed you and just kind of copy and paste this. But what I'm doing here, I'm checking, this is the not sign, right? If the x value that you want to evaluate is not the same as my last one, then I'm going to have to call my function here, this function here. So I'm just going to copy and paste this function. I got to reevaluate everything, which in this case is going to recall my structure function. Okay, so I'm recalling everything, and I'm going to now make these the last value. And I'm going to update my last x function. My last x function is going to be the same as my current one. Okay, otherwise, if x is equal to my last one, I don't need to call anything. I'm just going to give it my last value, so I don't have to waste time iterating. Okay, and I'm going to copy and paste this whole thing. The constraint is going to work basically exactly the same. I'm going to check, is this equal to the last one? If it isn't, then I need to call everything again and update all these values, update my x, update all of those things. If it is equal, then I don't need to call anything. I'm just going to pass in my last values. Okay. All right, so that was a bit cumbersome, but the upshot is that all of this stuff you could reuse. I wouldn't have to change this code at all. Well, we'll actually change it later in the semester when we add derivatives. But if I'm not providing derivatives, I could copy and paste this. I could use this template. This would work the same every time. The only thing I would change from problem to problem is this function here. Okay, this is going to be specific to my problem. Right here's where I actually define the function I want to call, and I populate the objective and constraints. But now I've basically, because I've done this, I've made it so that my problem works with the objective and constraints all being returned in one function. The other detail here is I actually have to put these shared variables before I call fmincon, because it's going to call these functions and not know what they are. So I'm just going to move them up here. But I could put them anywhere, or alternatively, I could have put fmincon at the bottom, and maybe I'm just going to do that. Yeah, how about I just do that? This then you can just, I'm going to put it at the, down here at just below these ones, for example. All right, so if I did that, I could make a line here, and I could say everything below this line, I never need to change. I would never need to change as long as I use these symbols, x0, lower bound, upper bound. These other two are already going to be the same because they're set here, and I'll have to use options. But other than that, I could just keep all of that the same. So I've basically got a little template here. Everything below, I just copy and paste. I don't change that. Here, I change, but depending on my starting points, bounds, and the objective and constraints for my given problem. All right, so another benefit of doing this sort of nested function here is that this is going to solve my other problem where I need to define parameters. So I can just define them here in this outer scope. I don't need to make global variables or things like that because it's an outer scope. Right, again, the colors just changed, meaning it's warning me or helping me see that these are now a shared variable. This is not a global variable. It's not available outside of this function or anywhere else. It's just only available here in this script. It's just the local variable for params is taking one from the outer scope because it's a nested function. So in this case, I think my parameters, this is going to be 100 from the Rosenbrock, and I think 3 from that quadratic constraint. So I can define those. Stress max, I could hard code it here. I could just define it. I think it's I can't remember what the problem was. This is actually these ones. Okay, so it's a 1 and a 5. You could think of these as, say, these were maximum stresses that these things need to be under. So I'm going to put in a 1 and a 5 here. Okay, so I think that should work. Let's run this, see if it works. Oh yeah, options. I don't have any options. And actually, I don't know if it's going to be happy if I just give it a blank thing. Oh, it did. It was happy. Okay, so it worked. But I actually do want to have some options. So let's put the normal option that we're used to using, or that we did last time. Is it optim options fmincon? I like to separate these line by line because we usually have a bunch of them. And I think it's display. And then I want to see all the iteration details. Yeah. Okay, great. So there it ran. It's very important when we run our optimization to look at these this message, and that's true of any optimizer you use. Just because you get an answer out does not mean that it's a good answer, right? It could have stopped for many reasons. It hit an iteration limit. You hit numerical difficulties. It couldn't satisfy the constraints. All sorts of things could happen. But here, this is a good message. It says the optimization is completed. The relative first order optimality measure, and it tells me that measure, that's this number here, the last iteration, is less than my tolerance. I don't know why it's going off the screen. It's a little bit annoying. And the maximum constraint violation is less than my constraint tolerance. These are the default tolerances, 1 e to the minus 6, kind of like we talked about in the video. So this output is nice to follow. This happens so fast, but normally what's going to happen is, let me just put in, actually I don't know what the syntax is for sleep in Matlab. See if that works. No, that's pause. Okay, pause. Yeah, I'm just putting in an artificial pause, just having it wait for 1 second just to simulate what would happen in a normal engineering simulation where it takes a little longer. So this is often what's going to happen when you're running your optimization. You're going to see things move by a little more slowly like this. This is why it helps to see this iter detailed so you can see if things are progressing all right. And maybe if things are going really poorly, you might have to quit and say, okay, something's wrong. So I'm seeing my number of iterations, for example, and each optimizer will, even if you change the algorithm, even in Matlab, you'll see different outputs. But iteration, this is the number of function calls. So this is how many times it's calling that structure function. Actually, more specifically, how many times it's calling this objcon function here. This is my objective. You can see it start out really big, 3,600, and it's going down and down. Feasibility, this is my constraints. These are supposed to be less than or equal to 0. So they started out at 17. It was infeasible. And you can see it pretty quickly got feasible. And now it's mostly just working on the objective. This is my first order optimality. We talked about that for an unconstrained problem. For an unconstrained problem is that I want the norm of my gradient to be 0. So I'm trying to drive all those gradients to 0, right? For a constrained problem, it's a little bit different. We'll learn about what it is later in the semester, but it's not enough just for it's actually not that the gradient should be 0 for a constrained problem. But this is something I'm trying to drive down to 1 e to the minus 6. You can see it start out really large. And finally, we got below 1 e to the minus 6. So and my constraints are satisfied. So I've completed the problem. That's good. Okay, so let's see. What were we going to talk about? We talked about parameters. Right? I can have as many variables as I want, especially if I do this nesting here. I should say, I probably want to return things from fmincon. I didn't actually write that in, so I should have done this in my copy and paste, like at least the optimal x and f. And then I'd want to return them, say, in this function here. So that when I call this, I can access them outside of this as well. Oops, cancel that. Let's get rid of this pause now. Okay, yeah, and then it runs really fast. And then I could, for example, do something like, just have this dumb name temp2, but then I can access, oops. I can access those variables right afterwards and see what they are. And I could call my structure from here. I could give it different parameters, see what happens. I didn't define those, but you know, I can call this thing now, right? Okay, so we talked about parameters. We talked about putting the objective and constraints in one function. Let's talk about these latter two. Okay, so options. There are a lot of options. Let's just pull up the docs. And actually, I'm just going to go to my browser since it's already open, but you can pull it up in Matlab. Let's say fmincon here. Let's go over to options. Options. Okay, here's a bunch of them. So I'm just going to highlight ones that you'll probably use. We're already using display. That's one I always use. Pretty much always have iter detailed on. Algorithm is one that can be useful. So let me move this over. Okay, we will talk about these algorithms later in the semester. The default, as it says there, is interior point, but it can be very helpful to try other algorithms because sometimes one will work better for a given problem and it's hard to know up front which will be best. So let's say I wanted to try this active set algorithm. That's another one we'll talk about. I guess I need to put the dots. Okay, and so I'm running that. You can see that the output here is actually a little different. And the error message, or not the error message, the completion message is a little bit different. It says different things, says max constraint, there's a line search step length. It's a little bit different output, and you can see the total number of iterations and function calls is actually different. This was actually faster. It's just a different algorithm. And so it's very helpful to have different algorithms at your disposal. We'll talk about some rules of thumb to maybe choose between these, but in general, you can't know which is going to be best for your problem. So it's good to be able to test. So that's something you'll definitely want to use. We'll get back to this later in the semester when we add gradients. This is something that will be very helpful. These tolerances you may want to change. There's constraint tolerance and optimality tolerance. They default to 1 to the -6, as we showed, but sometimes you may need to change those. Sometimes, especially with the optimality, you may not be able to satisfy to quite that tolerance. Let's see, finite difference, type, and step size. Again, these are things we'll talk about a little bit later with derivatives. You probably don't need to change them now. This is one you'll probably need to change. Maximum function evaluations. The default depends on the algorithm. It says it's 100 times the number of variables, except for interior point defaults to 3,000. That's not necessarily a lot sometimes, so you may want to change that and say, let's say I want to make it, 100,000 or whatever, something bigger, something that it's not going to stop. And max iteration, same thing. You might run into that limit. So just an example, let's say I put this at 3. I'm going to change this back to interior point. I'm obviously going to hit the limit. 3 is too silly. Let's do 10. Okay, and it gave me an answer, right? And this is the danger, right? That if you don't look, but it says it stopped because it exceeded the function evaluation. Solver stopped prematurely. And that's actually a link you can go look at and see some more information about that, about possible reasons. So this is something that will definitely happen at some point to you if you don't change it. So you want to increase that. Max iteration is the same, right? This is just the difference between these iterations and the number of function calls. We talked about that. Output function, we're going to talk about in a second. We're going to use that. These are things we're going to use later in the semester when we want to supply gradients. So we want to specify the gradients of the constraints and specify the gradients of the objective. Right now, since I haven't specified them, Matlab is just trying to estimate them using a finite difference, a numerical estimate. And so those are probably the main ones. So let's look at this output function. Okay, so this is something that can be useful sometimes. An output function says I can specify a user-defined function that the optimizer will call at each iteration. So I'm going to click that link. And so the syntax here is that I put an output function, and actually it looks like I can put many of them, but generally do that. So I'm going to put an output function, and I'm just going to call it outfun. Okay, so I have to give it a name, and it's a function I need to define. And here it tells me the structure of that output function. This is what it needs to look like. So I'm going to copy and paste that. And so what it does is every iteration it's going to call this. It's going to call it, and it's going to give me the X value of the algorithm at that current iteration. It's going to give me optim values, which has a bunch of data. It's basically the same as the data that you get at the end of the optimization, or that you can get, but I can get it now at every iteration. And so we're going to want that piece. So let's just write this function real quick. So I have a function, I just copy and paste that thing. Okay, so here's my output function. And let's see, what's in optim values? There's a bunch of stuff. So I can get things like, what's the constraint violation at every iteration? What's my first order optimality at every iteration? What's my function count? And I can keep track of these things. I could plot them, I could do different things. So more or less, it's kind of the stuff, or some of them are the stuff you're seeing here. And I could go in here and I could maybe copy and paste these things and parse it and get them and plot them. I could definitely do that. But that's going to be a bit of a pain, especially as these get bigger, and to manually do that. So I'd like to just be able to have a function that I can do that. So in this case, let's say I want to plot my first order optimality, that's my convergence criteria, as a function of either, let's say, the iteration, or let's say the function count, something like that. I could also plot the objective. So I'm just going to do those two. I'm going to do, let's say, iteration, first order optimality. So I'm going to do the same thing I did before. Since I've got already an outer function, I can initialize this. Let's say this is iteration. And I'm going to initialize these to some empty arrays. And when I get into this loop, I'm going to append to those arrays. I'm going to take what I had previously and I'm going to add to it. And I'm going to rename this because I don't want to type that long thing. I'm just going to call it OV optimum values. And the iteration is this one. It's called iteration. So I can just add that. So what I'm doing is every time this function is being called and the optimizer is going to call it every iteration, I'm just saving the number of, or the current iteration into this array. I'm just appending it and appending it. And since I've accessed it outside, when the optimizer is done, I will still have that populated. The other thing is I want to save my first order optimality. So I'm going to do that through this guy, first order opt. Okay, so now I've got those two things. Initially they are empty. When fmincon is running, it's going to call this every time, and it's going to just keep appending to these arrays. And stop is a flag that I could set to true or false. I don't generally use that too often, but it's something you could use, that if you had a criteria, your own criteria about when you wanted the optimizer to stop, you could define it in here. And so that's a useful way to add your own stopping criteria. So what I'm going to do is I'm going to add those as return values here, iter and opt, so I can access them after. And then let's just go now full screen to this. I'm going to call my function, and I'm going to now get out that history. Okay, so there they are. You can see I've got these arrays. Here are my iterations. Here's that first order optimality. I'm going to plot them, and note, these are actually exactly the same things that are here. It's this column here, it's this column here, but now I've got them from a function. I can get other things, even things that aren't displayed here. But these are ones I wanted, so I'm going to plot these. I'm going to plot this with a log axis on the y-axis because the optimality is changing across many orders of magnitude. Okay, so there it is. Let's put some labels on it so it's a little nicer. This is a number of iterations. This is first order optimality. Okay, so there's my plot. And notice again, the y-axis is changing across many orders of magnitude. Started quite high. This was our tolerance, 10 to the minus 6. So it jumped there in that last iteration. And we can see the progress. And this can be useful when you're comparing different algorithms, especially to see rates of convergence and such. It can also be helpful sometimes during an optimization to plot these things. So you could see, for example, how's my objective progressing, or how are my constraints, or this first order optimality? Am I flattening out? Sometimes you'll find that you get stuck and it's just becoming really flat for a long time, and you may want to terminate the optimization. So these can be helpful things to track. All right, I think we covered the things that we set out to do. So like I said, there was a lot of detail here, but you can kind of just copy and paste that from the Matlab sort of help on that, on combining objective and constraints. And then, yeah, be sure to check out the documentation output functions, but I think this should give you a good start to be able to do this on your own. All right, take care, everyone.